Okay, guys. As I said, I'm going to try to do a couple of videos for my absence, so it'll feel like I'm in the room with you. Try to have your the video open side by side with the OneNote that I have distributed to you, aptly called Newton's second law. Right. So on my last day, I spoke to you about Newton's first law, which is really if there's no net force acting on an object, it will keep doing what it's doing, or it will, if what it's doing is stationary, it'll keep stationary. If it's moving into constant velocity, it'll keep doing that. But what happens if there is a net force? If there is an unbalanced external net force, well, guys, it's going to accelerate. How much is it going to accelerate by? Well, that's what Newton's second law is all about. So here, this one here, the net force is 0, but in the second situation, the net force is 200. 200 in what direction? South. Always got the right direction, or you will lose marks, because it's a vector. It just makes no sense to not include direction. All right, so here, the net force is, in fact, 200 newtons south. Let's make the pen a little bit bigger. Okay. Now, typically it's written as a mathematical equation. The net force is equal to the product of mass and acceleration. So net force, now net, this is the Greek letter sigma, and you might have seen it in maths, the sum of. It's like when you work out the mean, it's the sum of the x values over n. It's the sum. You can put little fancy little things like that on if you want. It's capital Greek letter sigma, it means sum of. The sum of the force is always equal to ma. Now, of course, if you want to work out acceleration, this is probably the version that you'd use. You just got to rearrange that a little bit. So the acceleration is the sum of the forces over m. Okay, if the above car has a mass of 1.3 tonne, which as we know is 1,300 kilograms, calculate its acceleration. Pause the video and do it. Welcome back. How did you go? Well, hopefully you thought, well, the acceleration is going to be the net force, which we just worked out. 200, and 200 divided by 1,300 is going to give me something a bit like 200 divided by 1,300. I get 0.15 meters per second squared south. Don't forget the direction. And that's a pretty small acceleration. Obviously, it needs a pretty big force to really accelerate a heavy car in an appreciable way. Now, that's simple. If there's just one body and there's two forces acting on it, the bottom line is the big force take away the small force is always equal to ma. Okay, so the big force is always bigger than the small force by an amount equal to ma in every single case. Connected bodies, a bit more complex. What I've got here is a weight of 2.5 kilograms. Going over a trolley, you can imagine this. A rope going over a trolley, and that is attached, going over a pulley, attached to a trolley. And the whole system is going to sort of go that way, isn't it? We call it a system because it is more than one object. It's a system, but this entire system is going to do the same thing at the same time. So you can imagine a road train as a system, but there'd be a different tension force between the main truck and all the three cars it's towing compared to the force between the second last car and the last car. That'll be the smallest force because that force is only accelerating one of them. Yeah. So sometimes it's better to simplify a diagram, so I've just redrawn it here. Now, the question's asking, there's no friction, determine the acceleration of the cart. Well, we have to work out what is the net force. So there's only one net force, this guy here. The mass of the trolley is not providing a force that will accelerate this in any way, shape or form. It's just a weight down, but there's a reaction force up. It's got a weight down, yes it has, but there's a reaction force up from the ground. So that's not, its mass is not accelerating anything. But how many newtons is available for acceleration? Well, just that 2.5. And 2.5 times 9.8 is 24.5 newtons. That's how many newtons are available to accelerate this entire system. Acceleration is the net force over the combined mass. This 24.5 newtons needs to accelerate the entire 4 kilos. If the string wasn't there, it would just be accelerating the 2.5 kilos and of course be falling at 9.8 because 24.5 divided by 2.5 is 9.8. But this whole thing's going to be accelerating a lot less than 9.8 because the force is also pulling this trolley along in the horizontal direction. What have we got then? 24.5 is the net force. The overall mass is 4. And 6.1 meters per second squared. Oops, that is the acceleration of the system. Okay, system, don't forget, the whole thing's accelerating. Now, there's a slightly harder part, harder question. If a frictional force of 8.5 newtons acts against the cart, what is the acceleration now? Okay, so I've got an acceleration this way of 8.5 newtons. Not acceleration, a force, sorry. I've got a force this way of my 24.5 newtons, or 24.5 newtons. So my net force is no longer 24.5. My net force equals 24.5 subtract 8.5, which is 16 newtons, yep. So therefore the acceleration is going to equal the net force divided by the mass, in this case 16, divided by the overall mass, which is 4, 1.5 plus 2.5, 4 kilos. It's going to now only accelerate at 4 meters per second squared. That is because the force of 24.5 newtons needs to not only accelerate the whole system, it also needs to overcome the 8.5 newtons of friction. So the net force is only 16 now. Makes sense? Over here I've got a little bit of extra. Calculate the tension in the rope. What I'm asking here, guys, is there's a rope attached there. T. What tension is in the rope that is pulling that car? And this could be like the rope pulling, the linkage pulling a trailer or something. What's bigger? Clearly, T is bigger than the friction force. Agreed. And that must equal MA. I.e., what I'm really saying here is T take 8.5 equals now only 1.5 times the acceleration we just worked out. Why? Because I'm not looking at the whole system anymore. I'm only looking at this trolley that's got a mass of 1.5. It's accelerating at 4, so its MA is 1.5 times 4, and the big force take away the small force must always be equal to MA, so T is MA bigger. So T, 1.5 times 6, 1.5 times 4 is 6. I'm going to add the 8.5 to it, and I've got 14.5 newtons if I haven't made an arithmetic error. The tension is 14.5 newtons. A little way to test if that's really true, I could actually consider this. Well, this guy here must also have whatever force the tension is what's pulling up. The thing about ropes is that both ends have to be under the same tension. So if we think about the 2.5 mass now, let's just think about him. What's bigger? The force down. By how much? MA. Let's see if that's holding true. The net force is, for the 2.5 kilo weight, what do we know? The net force is equal to 24.5 subtract 14.5 equals 10 newtons. So therefore, we would expect the acceleration to be 10 over the 2.5, which is 4, which is indeed what we knew all along from the previous part of the question. So we've double checked that, and in fact you could have used this weight at the bottom to find the answer, because that tension is the same. Right here. Digest this, watch it again if you need to. Apparent weight. Have you ever noticed that funny feeling in a lift when it takes off, especially a really powerful lift, like a lift that's going to a really, really tall building in the city? You won't get this sensation in the lift in the science block. I've tried it. There's no point in us doing an experiment, all right? Now, I found a piece of clip art that I thought looked suspiciously like me on a skinny day. So let's imagine I'm standing on a set of scales in an elevator. Okay, and I'm just going to draw those scales in because I've accidentally rubbed them out. Here we go. So I'm standing on a set of scales like that, and I'm in an elevator. Okay. And what I'm saying to you is, these are a special set of physics scales, so they're calibrated in newtons. So just imagine, if G was 10, which it almost is, instead of saying 40 kilos, it would say 400 newtons. It would just be getting a bit of Tipex and putting a 0 next to all the kilograms and changing the word kilogram to newtons. If G was 10, it's not, it's 9.8, but just imagine it's giving a reading in newtons. So if it's reading 840 newtons, I wonder what that means Mr. Watson's mass is. Well, to me that's pretty obvious. Weight equals mg. Obviously that means mass is weight divided by g. In this case, 840 divided by 9.8. It'd be very different if I was doing this experiment on the moon. You would have to divide by 1.6, not 9.8. They wouldn't read anywhere near the same value. And I think Mr. Watson comes out to be 85.7 kilos. What happened there? 9.8. All right, that's my mass in kilograms. Now, show all labelled forces acting on Mr. Watson as arrows. So what I've got acting up is the force from the scales, and the scales weren't there, it would just be the force from the floor of the lift acting up. And I've, of course, also got my weight acting down. Now those vectors would be equal and opposite if there was no acceleration. For example, we're moving up at a constant velocity or stationary. All right, so we've done that. Now note that this normal reaction force is the reading on the scales and is what Mr. Watson experiences as his apparent weight. Okay, so if I'm accelerating up, it's going to read a bit more and I'll feel a bit heavier. If it's accelerating down, it's going to read a bit less and I'll feel a bit lighter. Okay, the elevator then accelerates up at a rate of 2. What force is bigger now, N or W? Well, clearly, if it's accelerating up, N must be bigger. I didn't label these naughty, Mr. Watson. N and W. N, because the net force is up. What is the reading on the scales? I.e. N, which is his apparent weight. Well, what do we know about Newton's second law? We know a lot. We know the sum of the forces is always equal to ma, i.e. the big force take away the small force is equal to ma. So in this case, the force up, the normal reaction force, take the weight, which I'll call it mg now, is equal to ma. So that's really saying N is equal to mg plus ma. And guys, you're always going to feel ma heavier or ma lighter in a lift or any fairground ride or anything like that. Ma heavier or ma lighter. And that's because the difference between the two forces acting on you is always equal to ma. So in this case, it is mg that I already know mg. It's 840. But I've got a little bit of extra here, and that is my mass times, what's my mass again? 85.7 times 9.8, which is 840, plus 85.7 times 9.8. So we're adding, sorry, I'm getting tired. It's past 11 o'clock, guys. That's not 9.8, that's 2. You spotted my deliberate error. Whoever did that, well done. Okay, 85.7 times 2 is, so it's an extra 85.7 times 2. It's an extra 171 newtons. And of course, that's going to come out to be about 1011 newtons. So that's what those scales will read when I'm accelerating up. Now guys, that a clever way to think about it would be, it's as if G isn't 9.8. It is 11.8. And if you were simply to go 11.8 times 85.7, of course, you're going to get exactly the same figure, 1011 newtons. Because if you think about this thing here, you could have taken m out as a common factor. It's m outside of G plus A. So if you're accelerating up, it's as if G is a bit bigger for you. If you're accelerating down, it's as if G is a little bit smaller for you. If these were normal scales, how many kilograms would they read? Okay, well here we go. I mean, we know weight equals mg. They're reading 1011. We want to know what they would kind of read. What mass would they give me? 9.8. It's not my real mass, it's just the reading, isn't it? So I've already got this on my calculator. I simply divide it by 9.8, and I've got myself 103 kilograms. Okay, which is about 10% heavier. That is exactly what you'd expect, because 2 is about 10% of 9.8. All right, so it'd be a slightly denser or slightly larger planet than the Earth. If we were doing this on the Moon, it wouldn't be 9.8, it would be 1.6. Now, calculate the reading on the scales in newtons when the lift is moving up at a constant speed of 5, accelerating down at 3. Let's do that, then I'm going to get you to have a little pause. In fact, I'm going to get you to pause now. Pause and just quickly have a go. Great. How'd you go? Well, constant speed, that's a red herring. The 5 doesn't matter, it's a constant speed. Constant speed is no acceleration. It's going to read exactly what it was before, which is 840 newtons. Yeah. Okay. Accelerating down is a bit different. Now you could be a bit sneaky and say, well, as Mr. Watson said, it's instead of being 9.8, it's going to feel like it's 6.8. You know, if you get it that well, then go for it. But I'm just going to show you the sort of logical, clear way. All right. So what have I got here? Starting from scratch, it's accelerating down, so the downward force I'm going to draw as a bigger arrow than the upward force, because the upward force, the normal reaction force from the scales, is going to be smaller this time. This time it's accelerating down, so the force down, which is weight, is bigger than the normal reaction force by an amount equal to ma. So the sum of the forces is equal to ma. Therefore, don't forget W is mg. I just don't like writing mg on diagrams. I'd rather write W because it's the symbol for weight. So I'm going to say mg take n equals ma. I want to find n, of course, so you can probably see how I'm going to rearrange this. It's as if I'm bringing n to the one side and bringing ma over, so mg minus ma. And that's what I said before, you either feel ma lighter or ma heavier. The lift is accelerating down, so you're going to feel ma lighter. Yes, you could take m out as a common factor, so it's m outside of g take a, which is really 87 kilos or whatever it is, times 9.8 take 3, which is 6.8. So the weight, the real weight, we do know, we were given this absolutely originally, it's the 840, because that is the 87 times 9.8, subtract, what's the mass again, 85.7, sorry, 85.7 times the acceleration, which is 3. You're going to feel a little bit lighter, aren't you? Okay, so if you're on the ball, you could just say it's 85.7 times the 9.8 take 3, which is 6.8. It's as if G is 6.8, we're on a lighter planet, it's going to be 583 newtons. If you got that, well done. If you didn't, watch this a couple of times so you really start to get it, okay? Okay, so you feel lighter if the lift is accelerating down. What if it was accelerating down at 9.8? This figure here would be 9.8. So this whole thing here would be 840. The net force, the normal reaction force would be 0. So you'd have a sense of weightlessness. So that you're in free fall, if you're in a lift that's in free fall and ignoring air resistance, you would be floating around in that lift having fun on the way to your death. But you could have fun on the way there. So if you're in a, that's how they do the comet vomit, that converted airliner that NASA used to simulate zero gravity. They go into free fall and everyone just floats around in it. Okay, here's one for you. Pause the video. I'm going to, it's worth 10 minutes. If this whole lesson takes 2 lessons, that's absolutely fine. Pause, go. How'd you go? Okay, so 2.5 tonne ute is towing a 1.8 tonne caravan. The ute experiences a constant frictional force of 300 and the caravan experiences a frictional force of 400. Shows labelled arrows or horizontal forces acting on the system. Now, the word system is important here. Okay, the ute van system. So the total force of friction is 700 newtons. So I'm simply going to do this, guys. I'm going to pick up an arrow and just have one dirty great big arrow, pull it. Alright. Dirty great big arrow. Going backwards. That's the force of friction. What is it? It's a total force of friction of 700 newtons. There's also the force from the engine and the ute going forward. Now, it would be the same size if you're travelling at a constant speed. If we're accelerating, it would be a bit bigger. It would be really big, you'd be accelerating a lot. If it was really small, that's when you're decelerating, you'd be slowing down. But I'm just going to draw it about that size. And I'll call that F, the force from the ute. All right, now, calculate the force provided by the ute when they are travelling at a constant velocity. Well, at constant velocity, the sum of the forces is equal to ma, which is 0 if you're not accelerating, and therefore the force is exactly equal and opposite to the friction. I hope you got that. If they're accelerating at 3.5, F must be bigger than the 700 by an amount equal to ma. Sum of the forces is equal to ma. So that means F take 700 is equal to ma. Now the mass, the total mass of this system is 1.8 plus 2.5 times 1,000, because we're in kilograms here. So I've got 4,300 kilos is the total mass that needs to be accelerated by this force, and the acceleration is 3.5. So therefore, I should have left a bit more room here. 4,300 times 3.5 equals 1,505 15,050 plus 700. Okay, so massive force is required just to accelerate a 4,300 kilogram combined unit at 3.5. Yep, so that is 15,050 newtons, and we've got the extra force of the 700 newtons, and of course 15,750 newtons is required to be applied by the ute to accelerate it at 3.5. That's a pretty big acceleration. You know, it's about a third of g, a bit more than a third. Now here's an extra for experts. The last thing for this lesson. Calculate the force applied by the ute to the caravan via the tow hitch when they're accelerating at 3.5. So to get us started here, I did just show you the picture separately. Okay, so you know, this is the force applied by the ute to the caravan through the tow hitch. Now that could be a rope if it was a car towing a car or whatever. And we've still got the force of friction pulling it back. And let's not forget that the system is accelerating that way at 3.5 meters per second squared. Okay, so what's bigger? This guy here is clearly bigger. I didn't draw him very well, did I? He's got to be bigger than that retarding force, the friction force, by an amount equal to ma. All right, so look, I'm going to call that T, as in tension. It could be a rope or cable. It's actually the tension in the towing hitch. And this force is the force of friction acting on the caravan only. So it's not 700, it's 400. There's 400 newtons pushing this caravan back. There's a force of T pulling it forward. The difference between those is always equal to ma. Sum of the forces equals ma. Therefore, now what's bigger? It's got to be T, because it's accelerating this way. Yep. T, take 400 equals mass. What mass? Just the mass of the caravan. 1,800. And it's accelerating at 3.5. So tension is okay, so 6,300 plus the 400. If there was no friction, the force would be 6,300 newtons, but there's also the force of friction that needs to be overcome, and that's 6,700 newtons. Now, as we did before, gentlemen, I could have worked out the force that the caravan's applying to the truck or the ute. Now, that would be less than this force by an amount equal to ma, and that would be another way to do it, because this force that the ute is applying to the caravan must be exactly equal to the, or in magnitude, to the force that the caravan's applying to the ute. Okay, gents, I'm getting a bit tired. I'll pause it there. I think now you can consolidate this by trying to finish all those questions in the Star Wars set on Newton's, not Star Wars set, in the textbook. I'll add those to the OneNote before I distribute it to you. I want you to have a go at the questions from Pearson on Newton's second law and do that for homework tonight. Thanks, guys. I'll see you virtually next time.